the motor circuit immediately after starting torque has been achieved. A high MFD start capacitor is used to create a high current flow and a large phase angle shift, providing a high starting torque. The capacitor must be removed from the motor circuit quickly. Otherwise, high current will overheat the start winding and may damage the motor. Either of two methods can be used to remove the start capacitor from a CS motor circuit. The mechanical method uses a switch that opens a set of normally closed contacts after the motor has started. The switch is usually fixed to the motor shaft and is operated by centrifugal force. When the motor reaches 2/3 or 3/4 of its rated speed, the switch contacts open and remove the capacitor from the circuit. This method is also used to switch out start windings in some motors, such as the one shown. The electromagnetic method of disconnecting the capacitor from the motor circuit is more commonly used than the centrifugal switch. A start relay, SR, has been placed across the start winding. Its contacts are connected in series with the high MFD start capacitor. When power is applied, the start capacitor provides a high torque to start the rotor. As the rotor speed increases, induced voltage increases across the start winding and start relay. When rotor speed reaches a preset value, induced voltage becomes sufficient to energize the relay coil. The SR contacts, normally in a closed position, open up, removing the start capacitor from the circuit. The capacitor start, or CS motor, has excellent starting torque characteristics, but is not as efficient as the permanent split capacitor motor, PSC. The PSC motor runs efficiently, but lacks the high starting torque of the CS motor. The motor shown combines the advantages of both. It is a PSC motor with a start relay and start capacitor. As the motor comes up to speed, the start capacitor is switched out of the circuit and the motor runs PSC. This combined arrangement is usually called capacitor start capacitor run, CSR, and is used to drive most compressors. As an air conditioning technician, you will sometimes be required to improve motor starting torque. Areas where brownouts occur are a good example. Start kits may also be warranted when a compressor keeps tripping on the overload and no reason can be found. Where a high starting torque is required, a hard start kit will be installed. Where low voltage or a voltage sag is experienced, a soft start kit will be used. Both kits contain a start capacitor and start relay. The difference is in the size of the capacitor. Thermistors are also used as soft start kits. A thermistor, or more specifically, a positive temperature coefficient thermistor, or PTC, is a temperature-sensitive device whose electrical resistance will increase as its temperature increases. The PTC thermistor is placed across the terminals of the run capacitor of a PSC-type motor. At room temperature, the PTC thermistor resistance is very low, perhaps 25 to 50 ohms. The application of voltage provides an initial surge of high current through the start winding because the low resistance of the PTC thermistor is effectively shorting out the capacitor. This surge results in momentarily increased starting torque to turn the rotor. The temperature increase created by the high current causes the PTC thermistor resistance to increase very rapidly, removing the short from across the run capacitor. The motor then runs as a normal split capacitor motor. Now we will discuss the construction, operation, and applications of the shaded pole motor. The visual shows a 4-pole motor, which is simply a rotor pivoting within 2 pairs of stator poles with the stator coils connected in series. A groove separates a small portion of each stator pole from the rest of the pole. Banded around this smaller section of pole is a piece of metal, which, as we will see, provides the phase shift needed to start the motor. In the shaded pole motor, the metal bands cause the buildup and collapse of the magnetic fields at the large main pole and smaller pole to occur at different rates. During the period of unequal magnetic strength, torque is exerted and the rotor turns. Shaded pole motors require low starting torque, but their speed control under varying load conditions is poor. They are not as efficient as PSC and lack the torque of CS motors, so they are used in light-duty applications such as running blowers in small air handlers and heating units. You should now have a good working knowledge of single-phase motors. They are usually classified by operating characteristics. Their characteristics, applications, and relative cost are summarized here. As an air conditioning technician, you should have a good understanding of how these motors work and how they are used in the industry. Three-phase motors have certain advantages over single-phase motors. First, their rotational direction can easily be changed by reversing any two of the three supply voltage wires. Second, they exhibit less running torque pulsation, since at least one phase is always producing an induced rotational effect on the rotor. Third, and probably most significant, three-phase motors have a higher starting torque than single-phase motors. Finally, three-phase motors are more efficient than single-phase motors. As a class, three-phase motors are a lot easier to understand than the single-phase variety. A rotating magnetic field is achieved by placing the stator fields 120 mechanical degrees apart around the motor shell. With a three-phase power supply, voltage inputs are separated by 120 electrical degrees. Application of these separated inputs to the stator coils results in a rotating field. Because of this phase difference, three-phase motors create their own starting torque. Therefore, start windings, start capacitors, and start relays are unnecessary. Three-phase motors are wired in either a delta or Y arrangement. The connections for these motors are similar to those for the distribution transformers that you studied earlier. In the delta connection, the voltage between any two lines to the motor is the same as the voltage across each phase. However, current flow in each line is 1.732 times greater than the current in each phase because of the series parallel arrangement of the circuit. In a Y-connected three-phase motor, phase voltages are less than the line voltage, and phase currents are the same as the line currents. Each voltage phase provides current for two windings connected in series. This results in different phase and line voltage and current relationships than those for the delta connection. Differences in line and phase limits dictate that there will also be differences in power provided to and consumed by the delta and Y-connected motors. Power for either connection method is calculated by use of the following equation. P equals 1.732 times E times I times power factor. You can see that there are significant differences in power consumption for the two types. The ratio used, 1.732, is the square root of 3. At this point, you have been acquainted with the various types of electric motors you are likely to encounter as an air conditioning technician. You understand how they work and how they are selected to perform various jobs. An important thing to remember is that motors are among the most expensive components in the systems on which you will be working. Therefore, great care is taken to protect them from damage. The most common cause of motor failure is excessive heat. Heat can be caused by a variety of problems, such as a defective start relay, excessive load, or loss of refrigerant gas cooling in a hermetic compressor motor. Motor protection devices are designed to disconnect power from the motor before heat failure occurs. Let's look at some additional causes of overheating. Every electric motor has an electrical characteristic called locked rotor current, or instant of start current. Before the rotor starts to turn, there is an instant when the current is 3 to 5 times its normal level. If that surge is sustained because of conditions that keep the rotor from turning, the motor could be severely damaged. For that reason, overload protection devices are needed to disconnect power if high current causes an overheat condition. Another cause of excessive heat in motor windings is operation at too high or too low a voltage. Motor overload devices must be capable of protecting against high temperatures caused by voltage variations. Here are the motor terminal voltage variation tolerances